Okay, so let me start with now part 2. So Luca wrote for me this stuff at the morning. So Luca gave nice introduction to current classical and quantum volumes. And basically, I will continue to work in this setup. So most of my stuff, I will think about Calabi-Yau. So I will have C of R3 quotiented by U1R. And then, so what Luca was explaining to you at the morning, that there are two objects in game. So you will have some, volumes here, equivariant volumes of the manifold X, which is, you heard all discussions today at the morning. And then here, you would have some, what we will call quantum volume, Fd of epsilon, I don't know, let's call it X, okay? There are limits, there are issues, etc., and that has been discussed at the morning. So now, and of course, these guys, as Luca told you briefly, you can extract genus 0 Gromov-Witten invariants, so closed. So this is a genus 0 closed Gromov-Witten. And what I will discuss in this game, how to extract open, and actually there is some very nice twist to this. So we are working here. So my main goal for you now will be basically to discuss this notion of symplectic cut, well, which is actually, there is also symplectic gluing. And I will tell you how these notions appear in this picture and how you can extract open stuff out of doing certain manipulations. So symplectic cut, symplectic gluing, I think was introduced by Lerman in 95. And instead of giving you formal definition, I will basically start to draw for you some pictures and try to explain what is going on. So my basic example will be, let's take C2. Okay, so my toric diagram for C2, I can just draw this quadrant, and I have, a T2 vibration, and when I hit this this boundary, my torus degenerates in appropriate sense. And of course, on C2, I will have U1 acting on C2, and I will just pick up diagonal actions. So I will adjust my zeta 1, zeta 2 diagonal action. And of course, for these guys, I would have a moment map, right? So for this section, I will have this obvious moment map. So imagine that I take on this plane and I draw for you the my value of moment map here. So this corresponds when my mu is equal to C, to some value of C. Okay. So of course the map is just hyperplane. So if I look at this map here, then this part of space, so the map itself, this is just S3, right? So what's inside of this is a ball, and outside it's more or less a 3 times line. So the whole idea of symplectic cut, that I would like to cut my manifold, but I would like to cut in such a way that my building blocks are symplectic manifolds, okay? Of course, you know very well. So when you look at this picture, it's very, if you think about toric diagram, it's very clear what you are having here, right? So if I have a toric diagram of C2, then what's staying here, this is a toric diagram, will be of P2. And this is toric diagram will be O minus 1 over P1. So if I we have to make this precise, but if I stare at this picture and it would make sense, then somehow, my symplectic gluing, which is very obvious at the level of toric diagrams, will be the following. I would like to represent C2 as a gluing of P2 ln of P1 with O minus 1 over P1. So how would I do it? So basically what I need intuitively, right? So I need to take my torus, and then I have to require that it degenerates along this line. So I need to require these degenerations, and then it will give me P1, and then it will give me P2. Of course, if I don't look at C2, this looks as a singular space. I will discuss these issues a bit later. So let's discuss it. So how do I get this space, for example? So let me take another space C, zeta, which would be C2 times C. And I will introduce my symplectic form just so. In principle, this can be any symplectic manifold. So basically the symplectic cuts are defined whenever I have my symplectic manifold, I have U1 action and I have a moment map, and I want to cut along the certain values of moment map. Let's make life simple. I'm in a Köhler world, okay? So this exists, you don't even need actually U1 action, you need a local U1, etc., etc. So you need much less structures, but I'm making life very, very easy. So I'm not going to discuss any complications, okay? So I'm taking this symplectic manifold, I put C, and then I can define for you extension of this sort of bigger symplectic structure in a rather stupid way, something like this I dw h dw bar. Okay. And then what I can do, I can define to you this space P mu plus, which would be zeta quotient by U1. Namely, I will write to you my moment map minus W bar. So by the way, what I'm doing is I will extend my action. So I extend my action by -1 here. So this will act by, so my U1 on C will just basically act by W sending to E minus alpha W. And then I get C. I will do two choices. So if I put here plus, I will get upper space. If I get minus, I will get another space. Because you see, when I'm doing these things and I want a quotient by U1, so if I look from point of original space, I bring this stuff to another side. So I will get mu C plus W square. So I'm looking at the values of my moment map, right? So on my moment map, mu is less than C, right? Sorry, other way around, yeah. Okay, so it means that I'm looking now at this part of the space, right? Because if I draw my moment map equal to C, and this space is up there. And then I have to quotient by U1. What is going on, basically, what I will do is exactly, if I quotient by U1, I take this space and I contract my circle. Okay, so this, I can do this choice. And then another choice would be just to take m bar minus and construct now another space with U1. When I will take mu plus W square equal to C, quotient by U1. And this exactly will correspond now, would be C minus W square, and I will get mu less than C. So this will be this part of the space. So again, what I want to do, I want to cut the space, and then I want to contract along the boundary. I want basically make a quotient by S1, because then it would guarantees me that I'm gluing two symplectic manifolds. So my circle will shrink on the boundary, and this is exactly what I want to do at the level of diagram. Okay. Right. Because, yeah, I want to avoid, I mean, what I'm trying to tell you is the following thing. So at the level of toric diagram, right, you can draw the straight lines. Now the question is, you want to do sense of these lines in a bigger space, right? So for example, if I draw to you line with not rational coefficient, this would be crazy. I cannot make sense. So I have to draw a line only with partial coefficients. And then I want basically to do a quotient and to identify with you gluing. So here what I'm doing, right, in this particular case, I'm getting for you these spaces. Because if I look at this space and this example, my moment map will be the following. This will be zeta1 square plus zeta2 square plus w square. And I'm doing the things, and I'm quotienting by u1, right? And I get a p2. When I'm doing now this on opposite side with another choice of the sign, and I'm quotienting by u1, I will get correspondingly O minus 1 over P1. So for me, it's important that I get actual spaces. Okay. And then typically, if you implement the quotient along this line, of course, I just get P1. And that's exactly what people call symplectic cut. So you're cutting C2 along P1 in two pieces, P2 and O minus 1 over P1. And of course, you can glue in them, etc. At the level of toric diagrams, it's a very trivial operation. You just draw appropriate lines, which corresponds to actual moment maps. At the level of symplectic manifolds, you just construct them. And what's important that you take a symplectic, you cut, and you get two symplectics, and you glue along symplectic. Okay. So let's stick to this example and let's discuss, I mean, what's the point about this thing. So what we would like with you to ask the following questions. What's going on with this story with respect to these operations? So I will give you another definition of symplectic gluing later on, but for now is this one. So again, you can do a more general example, but divisor what? Of course, when you glue them, you will glue them along the divisor, right? Absolutely, yeah. Right. So we have with you this picture, right? So we cutted things along P1, and then we have O minus 1 here over P1, and then we have P2. So what's important in this diagram, what I have to put on the top of the things, I have my U1 actions, right? So I have U1 actions acting like this, and I have U1 action acting like this. So let's calculate with you. So Luca explained to us how to calculate equivariant volume of epsilon t, for example, for P2. So you write this Jeffrey Kirwan guy, right? And you will get E phi of t, E epsilon 1, 5, epsilon 2, 5, and then there will be epsilon 3, 5, but because I don't have any here other symmetry, I will just put plus phi. So I put epsilon 3 to 0. You will see later on why, okay? So I do the things, and if I calculate this integral, there will be 3 poles, phi equal to minus epsilon 1, phi equal to minus epsilon 2, and phi equal to 0. So if I do the things, I will get the following stuff. Minus epsilon 1 t, epsilon 2 minus epsilon 1 minus epsilon 1, plus E minus epsilon 2 t, epsilon 1 minus epsilon 2 minus epsilon 2, plus 1 over epsilon 1 epsilon 2. Okay, this is one calculation you can do. Then let's calculate another piece from this guy according to this prescription, which Luca explains. So we can calculate now for So let's calculate now the volume of epsilon t O minus 1 over P1. So look at it for O minus 2, but I mean, this is more or less the same as before, but with just different things. So you get this epsilon 2 plus phi. And again, because I don't have in this picture epsilon 3, I would just put minus phi. So this minus corresponds to this minus here. So now I take only two poles. I take this pole and I take that pole. So if I'm writing to you the things, what I will get the following: minus epsilon 1 t, epsilon 2 minus epsilon 1 plus minus epsilon 2 t epsilon 1 minus epsilon 2 epsilon 2. So now if you stare at these two things, these two terms and these two terms identical up to the sign. So what I can do for you the following. So this is just very trivial observation, but what you can see that this guy plus this guy, so volume, equivalent volume of epsilon t over P2 plus equivalent volume of epsilon t over O minus 1 over P1 is equal equivalent volume of epsilon over C2. So Jeffrey Kiron is knowing everything, so you can glue the volumes. So if you have a symplectic kite, you calculate volume by this prescription, you calculate volume by this prescription, you sum them up, these two terms cancel out, and you get C2. So for example, if you start to expand these guys, so these things, for example, will look like, as this is compact manifold, this will be 1 over square root of, 1 over 2 T2 plus terms of order of epsilon. If you expand this guy, then this will be 1 over epsilon 1, epsilon 2, minus 1 over 2 T square plus 0 of epsilon. So for example, I remember a couple of years ago, Marshakov asked me, when you calculate the volumes, why do you get here minus? I mean, what does it mean that you get for non-compact space, you expand, you get minus? So this is very, very important. The formulas are organized in such a way that all these terms cancel with these terms and you get exactly this thing. So this minus is very, very important. So in a way, intuitively it's obvious that basically equivalent volumes are some objects you identify with the things, and it's compatible with cutting and gluing. Of course, it's important thing that it's compatible in cutting and gluing, that when I glue the spaces, I have to identify correctly my epsilons, because you see here in both calculations, I don't have epsilon 3. This is not end of the story. So this is first statement that my two volumes are equal. Now let me write to you another object here. So volume of P1. So what's the volume of P1? Right, so again, following what Luca told us, we have this guy, epsilon 1 plus phi, epsilon 2 plus phi. You calculate this guy, you will get E minus epsilon 1 t, epsilon 2 minus epsilon 1 plus E minus epsilon 2 t, epsilon 2 minus epsilon 1. Now, if you stare at this picture, what would you expect? If you have this line, and you take this line, and you drag this line all the way to origin, and you integrate this out. Of course, you would expect that by integrating the volume of P1 and dragging everything up to the corner, you should get a volume of P2. So this is, again, very trivial calculation to do. So what's the statement? The statement is the following, that if you want to get a volume of epsilon t of P2, this is integral from 0 to t of dy, a volume of epsilon y of P1. So I just invite you to do this integral now. So you put here y, you do this integral, and you will get exactly this guy. Sorry, I have a, what do I have? Minus sign here. Oh, sorry, yeah, it's 1, 2. Yeah, thank you. So this you can just sit down and check. So I mean, this is very, very trivial calculation. So you will get E minus epsilon 1 y, epsilon 2 minus epsilon 1 minus epsilon 1 evaluated at 0 t plus epsilon 1 and epsilon 2 is exchanged. And then you can get this formula. Of course, now you can do another thing. You can take this line and drag all the way to infinity, and then you will get something else. So you will get that volume of epsilon t of O minus 1 over P1 can be written as integral from t to infinity dy volume of epsilon y over P1. Again, you can check it. So now I evaluate this at t at infinity. Again, in all these calculations, I will assume for convergence of original integrals, I typically assume that real part of epsilon is positive. That was built in the formalism which Luca was introduced at the morning. Okay. Yes. It's so trivial calculation, right? I mean, what I'm telling you that, so when you look at diagram, right? I mean, what I'm telling you that I'm equivalent volume, so it will be just giving you, so the volume of 2 will be 1 over 2 t squared, right? Now I'm making equivalent extension of this object. So I identify some notion of volume here, identify notion of volume here, and I'm saying is that, you know, additive. So with respect to U1 symmetries. I mean, the question is, I don't want to say that this is profound insight, but, you know, it's very simple. Sorry, I don't understand. You just do two calculations, they agree, right? I agree that from the calculations you can see they agree. Right. Is it also true that you think before the calculations that they agree? It depends on your, I mean, look, you and me, we are living in this different world, so I don't know what's, you know, you're asking. I'm saying, you know, I do calculation to understand it. Then some people will say this is obvious, right? I drew the line, I add two fixed points, and I subtract them. And basically, these two fixed points for P2 and these two fixed points for this manifold comes exactly with opposite sign. I mean, of course. Well, wait. Hold a moment. I mean, this is not such a simple union. I mean, that's what people invented this symplectic cuts. It's not something that you cut a manifold in two and you do it. No. I mean, this is what I told you. If I cut by moment map, I get a ball and I get a 3 times line. What do you integrate there? It's right. No, right. But what's important that this additivity respects U1 actions. I mean, that's what maybe, of course, if you will do this additivity, right? So I can do symplectic cut in compact space like this. And what I'm telling you that the volume of this plus volume of this will be this. It's a very trivial statement. Now I'm saying is that the same statement will work when you have compact and non-compact spaces and you take U1 actions in the count appropriately. That's the only thing I'm telling you. Again, I don't know, you know, to me right now, it does not look such a deep statement, but I never found it in the math literature stated in any clear way. But again, whenever I talk to mathematicians, they either for them everything is obvious or not. So I do calculation, I get my result, and you guys do whatever you want. Okay. So this is two properties. So in a way, what's important? Again, this is what I like to call it categorical definition of equivalent volumes. So presumably you can define the equivalent volumes as something concrete functions on Cn, and then it will be compatible with all these manipulations here. Because what's important thing here, that if I take a volume of P1 and I integrate from 0 to infinity, so I drag P1 through whole C2, I will get a volume of C2. But this is just means that if I put a delta function, which Luca was putting, and integrate the delta function over all the values of, moment, allowed values of moment map, I get identity. So this is sort of trivial things in a way at the level of formulas. Okay, so this is of symplectic cut story. Right. Of course, yeah. This will work whatever you cut lines. It's important thing that it's a decent moment map. So the danger is the following, that everything will be screwed up if my line is, for example, has whatever irrational coefficients. It will not correspond to any U1 action. So all this formalism, which Luca was telling you, will fail. Okay. Good, so again, I'm not claiming that this is some profound thing, but what we want with you to understand, we want to understand what's going on with this type of things in a quantum setting. So in quantum setting, what you have to be prepared that in a way we would like to keep some elements of these things. So there are a lot of statements here. So I'm telling you two types of statements. I'm telling you that volume of this space plus volume of this space equal to everything. And another statement is that if I take this space and I drag here, I get the volume of this. If I take this guy, I go there, I get volume of here. So in quantum world, I cannot expect that all these properties will work simply because if all these properties will work, I will end up again with equivalent volume. So something should be given up. And moreover, all these manipulations you will see actually give us open string stuff. So, sure. In particular examples, maybe, but I don't know. It's the thing is that there are more complicated setups, which I'm not sure I can repeat what you exactly saying. Okay. So now let's try to go to Calabi-Yau. So I will work out some example first and then make a claim, and then let's see how much time I will do that. So now we like Calabi-Yaus, right? So let me do C3. So what else I can, easy I can do. So and for C3, I have three, so my equivalent volume, so the volume of C3, this will be just 1 over epsilon 1, epsilon 2, epsilon 3. So then I need some cut. So let me just say that I'm choosing U1 acting on C3 in the following way. I will tell you that my zeta 1, zeta 2, zeta 3. So I don't touch zeta 1, and then zeta 2 goes with E alpha, and this goes with minus I alpha zeta 3. Okay? So my moment map for this example will be just simply zeta 2 square minus zeta 3 square equal to C. So now I don't know how to draw a picture for you, but what I will get, I will have something P1 here, zeta 1 square, zeta 2 square, zeta 3 square, and now I have a plane here which cuts my space. Okay. So first we can repeat the classical calculation for this cut and then do quantum calculation. So now again, always remember that when you will do this calculation, for example, if I want to calculate equivalent volume, so this defines me cutting manifold into pieces, and I want to calculate equivalent volume to the right and to the left of these guys, and this will be tricky depending on the it's positive or negative because there are different chambers. So what I can do, I can just, let me call it C epsilon. This would be my volume for this space. So this is analog of P1 now. This will be 1 over epsilon 1, and then I just write this integral I phi t epsilon 1 plus, sorry, epsilon 2 plus phi, epsilon 3 minus phi. And then depending on the values of C, I will pick up, for C positive, I pick up this pole, for C negative, I pick up this pole, and then of course what you will get correspondingly two values. So for C positive, you will get something like this, E minus epsilon 2, C epsilon 1, epsilon 3 plus epsilon 2. And then for C negative, you will get E epsilon 3C, epsilon 1, epsilon 3 plus epsilon 2. So this is a equivalent volume corresponding to this plane or to Calabi-Yau twofold. Now, if I take this guy and try a drag on, right? So if I take this guy and integrate out, so what do? I will take integral from minus infinity. So this plane now can be drag on for all values of C. So C can be minus infinity to plus infinity. So I drag this guy and I will get this thing. So I will write E epsilon 3C, epsilon 1, epsilon 3 plus epsilon 2 dc, plus I have to substitute another expression. So all this cutting and gluing works, but you have to be aware of different chambers when you do this calculation. Epsilon 3 plus epsilon 2 dc. You do calculation, of course, you get something what you would expect. Okay. Okay. Now let's do a quantum version of this. So the quantum version, again, what is FD, what would be quantum volume of C3? I would define it like this. It's a gamma function of epsilon 1, gamma function of epsilon 2, gamma function of epsilon 3. And if anyone is interested in quasi-maps, I can privately explain why it's good counting. It's equivalent counting of certain maps. But let me postulate it. So this would be my quantum volume. So this is quantum volume for C3. Then I have this plane, and I'm just following the prescription which Luca gave. So I would define my quantum volume for this plane to be correspondingly gamma of epsilon 1. So there will be this quantum Jeffrey-Kirwan prescription, and then I will have d phi, and then I will have E phi c, gamma of epsilon 2 plus phi, gamma of epsilon 3 minus phi. And then again, this prescription would depend if my C is positive, I take this tower of poles. If my C is negative, I take this tower of poles. But whatever you do, the answer is the same. So the answer, if you perform this integral independently of C, what you will get the following function. So you will get gamma of epsilon 1, gamma of epsilon 2 plus epsilon 3, E minus epsilon 2C, 1 plus E minus C, epsilon 2 plus epsilon 3. So you can, of course, pull it out here and also get epsilon 3. So this is a feature which Luca was telling you. Once you start to calculate quantum volumes, the chamber structure is not important. Now what's going on that this expression has two different semiclassics. So for C positive, you will get these terms as a leading semiclassic origin. When you go to C negative, this would be a leading term to semiclassics. But as a function, this is the same function. Okay. Good. So then next thing what you can check, again, this is sort of triviality in a way. Let me see what I wanna. So next thing, if I drag this plane over whole space, even in quantum world, I would expect that I will get a quantum volume. So you can perform this calculations, take FD for C3. So this is, sorry, I switched to the notations which we use in the paper. Epsilon 3, and this is equal just dragging the plane HD over C epsilon DC. So if I take a quantum volume of the whole plane and I drag through whole space, then I will get an original quantum volume of my C3. And again, at the level of gamma function, etc., it's in a way trivial manipulations because it's integral of a delta function, etc. So, however, what I can do next things, I can split, so I can fix C, and I can split my sort of space in two parts, and I can define for you. So I'm basically telling you that I can, if I think about this as cutting by these two spaces, I don't know, x plus bar over x0, x minus bar over 0. So then I can define for you this object, fd, I think less than 0, c epsilon. So I will write for you the integral from minus infinity to c, h of d s epsilon ds. So I'm dragging plane only from c to minus infinity, I get this object. And then, of course, I can do in opposite way from c to plus infinity, have this integral. Now, let me make one statement, is that these objects are identified to the left of this plane and right of the plane, but it would be very misleading to call this guys quantum volumes. It's something else. Okay, because if I would request all properties to be satisfied, then I will end up with classical volume. So a priori, if I draw this plane and I look at the space, I can realize this is variety, and I can look at its Picard-Fuchs equations. But the Picard-Fuchs here and these objects are slightly two different things. Anyhow, you can perform this integral. So if you perform this integral, then you get some function. So let me roughly write for you this function and then try to make a statement. So what you get, if you perform this integral, you get this sort of half volume fd of c epsilon. This will be some beast, which was gamma of epsilon 1, gamma of epsilon 2 plus epsilon 3 over epsilon 3, e of epsilon 3c, 2f1, so it will be some hypergeometric guy. Epsilon 3 plus 1 minus ec. Then what you can do out of blue and define another object here, which let me call wc epsilon, which you can think as some monodromy of this guy, so something like this 1 over 2 pi I f d plus or minus c plus pi I epsilon minus fd minus c minus pi I epsilon, right? So alternatively, I can write for you these guys. So this is the same as now contour integral from C minus I pi, C plus I pi of HD. So I'm now, what I'm doing before my C was real. Now I'm going to complex plane and I'm doing this integral. So you will get this function. And if you start to expand this function and look at structure, then it looks the following. Again, it's the example I'm telling you is very trivial, but I don't want to go to non-trivial for examples because it will be too long to write. So now the statement is the following, that if you take this function and try to write, expand this in epsilon, so you will get something singular, which you have to know how to extract, and Luca was addressing these issues, and then you will get something regular here. And what do you get as a regular? You get this object, Li2 of minus EC plus 0 terms of order of epsilon. So this is open stuff. So this is open Gromov-Witten invariants associated to certain discount to associated. So now let me make a statement, and let me try to explain this a bit more proper. So the idea would be the following. So this would be the main statement of our story, that you have a Calabi-Yau. So then I will tell you in a moment there exists certain dictionary between toric Lagrangians and symplectic cuts. So if you take a symplectic cut and basically you calculate either monodromy of these half volumes or contour integral, then it will actually give you open this superpotential from which, if you expand an epsilon, you will always extract open Gromov-Witten genus 0. That's a statement. And I think we can prove it in general. So I think in the paper which on the net, we did some examples, including like local P2, etc. But I think we more or less understand how to prove it in general. So let me try to give you some more abstract statements. That's a good point. Actually, I don't understand the proper physical thing. I don't know if there is available, and if anyone knows, GLSM type of description for open stuff. But I think physically, if you ask physically what corresponds on this picture, I don't know. If I have time, I will tell you about Calabi-Yau fourfold. But to be honest, I don't know. So we observed this by accident. This is experimental science. I don't know how to, and then we are trying to prove this in hard way. But of course, to get a physical intuition, this would be extremely valuable, but I don't know. And I don't know any GLSM type of calculation for open string stuff. Maybe it exists, but I'm just simply unaware of this. So let me try to make a statement, what are we calculating? And let me make another statement that it's important in all this game to have equivariance. So only once you have a fully equivariant answer and you expand it, you will recover a relation between open stuff and closed stuff. If you kill equivariance, then you lose everything. Because all these epsilons, all these monodromies, work with epsilons. And only after you expand and you get usual stuff. So let me try to explain to you the statement, which we so we are working on toric Calabi-Yau threefold. So we have CR3 over U1R. And if you go back, I don't know, 20 years ago, then there is the following way. So you can define a fine line with a slope 1, 1. So you define this in a bigger space. So you write this as follows. You write I from 1 to r plus 3. And then you have qi1 zeta I square equal to c. So this will be typically H1 condition, and then there will be condition H2, which I can write as a qi2 zeta I square equal to 0, I from 1 to r plus 3. So typically you get this line, and then you fiber torus over this line with the conditions that theta 1 plus theta r plus 3 equal to 0. And we know that under this quotient, I mean, these guys plus this descent to special. So this is descends to special Lagrangian manifold, which preserves still T2 action. So sometimes it's called toric Lagrangians. Okay. And now here, typically with this, when you write these two constraints, you can always take this constraint and add it to this with some integer. I'm not going to discuss it, so I'm very, very short on this, but you can do these things at here when f is some integer, and in this literature it's called framing. And of course, for toric Lagrangian, there is also some local system, etc. But the statement would be the following, which we're interested in, is that there exists a correspondence between framed toric Lagrangian and a symplectic cut. Well, it's not arbitrary cut. I mean, it's what we call Calabi-Yau cut. So it means here one of the important conditions to preserve that it's special. Some of these q's alpha I from 1 to r plus 3 should be squared to 0. Sorry, should sum up to 0. So it means that it's like in previous example, when I do the cut for my plane, it's important that charges sum up to 0. Of course, it's not the most general cut, but it means that when you look at symplectic quotient corresponding for Calabi, still it's a Calabi-Yau basically. So we look at these symplectic cuts, and you can identify them with a toric Lagrangians. Then the story is the following: that if you take this cut, and you will, with this cut, identify this HD of T, C, epsilon. So this would be a quantum volume of Calabi-Yau twofold. So this symplectic cut will define you that your Calabi-Yau is cutted in pieces. This guy, then there will be x0, and there will be this guy. So Calabi-Yau here, this is what I call x0. And then, for example, you can take these guys and integrate half volume and look at this monodromy, but alternatively, you can say that you just take this contour integral and define this object C minus IP, C plus IP, and then you will have HD, DS. And the claim is the following, that if you take this W and you take singular part apart, so you look at regular part plus terms of order of epsilon, this is always open string genus 0 Gromov-Witten for this Lagrangian in a fixed framing. So as you can imagine, that outside of simple example, this becomes pretty complicated, but basically this is the world of whatever hypergeometric functions Lorentz hypergeometric functions, etc. But you can always extract the thing. So this is a statement. You have frame toric Lagrangian, you get symplectic cut, you calculate quantum volume for this guy, x0, then you can calculate this object, and this, if you extract regular part, then you get an open string count. Any questions about this? Sorry, well, basically, so what's a toric Lagrangian? So you have to take a fine line up there. So you take a fine line, which is given by two conditions. So one typical condition that you take a sum of this plane, which equal to CC, it's typically open string moduli. It's where your plane is located, and this sum up to 0. And then there is a theorem that these guys descend down to Lagrangian. But this framing, you can add these conditions to this all the time. So typically the cut corresponds to, to Lagrangian plus choice of this framing. I don't know, it's a long story. I don't want to go there. So this example, which I gave you before, so if I go to C3, and then I wrote to you this plane zeta 1, 2 minus zeta 3 square equal to C, and then I think you have, no, I don't remember what other conditions we have. So Lagrangian is its particular line. So within this plane, right? Within this plane will sit a line. And this line will have a torus vibration T2, and this what corresponds to Lagrangian. This is what's going on. So this line corresponds to Lagrangian, will sit within this plane. And then you sort of can move this, of course, when you have a line, you can move the plane. Yeah. I mean, there are a lot of issues, which I don't want to go at all, dependence from the framing and stuff like this, but this can be taken care of everything. Exactly. And then, of course, you can discuss what's going on when you change the framing. So you keep this line, but your plane is changing. So then it's also pretty well under control. Okay, so maybe in remaining like 10 minutes or so, so let me try to tell you a different story. So the problem is this symplectic cuts, when you look at, three-dimensional Calabi-Yau, right? So this is what I wrote here. So when I'm actually trying to write this for your formula, if I think about spaces, this looks sort of weird. I mean, it doesn't mean so. If I try to glue actually two spaces along this space, this looks like a singular space. So there is exist of representation of symplectic cut due to Braverman construction. So this is Braverman construction for symplectic cuts. He did it for Köhler manifolds. Basically, what will happen that I will construct for a bigger manifold, And basically, this space will appear some degeneration. So I will have some fibration, and it will appear to get degeneration. So let me try to tell you what's going on. So imagine I have my quotient, right? So I have a CR plus 3 over U1. Of course, this is not related to Calabi necessarily, okay? And then what I will do for you, I will, so I have this data, and I will have this moment maps, which is the ones which Luca discussed in the morning, right? And then I will have another guys corresponding to the cut, right? So to the cut, I will have this condition C is equal to sum over Qi zeta I square, I from 1 to R plus 3. So this would be a cut. Then I can encode this data in the following. So I can construct a bigger manifold for you by doing the following thing. So I take C R plus 3 times C plus times C minus, and I will quotient by U1 R plus 1. So my charge matrix will look as follows. I will have Q 0, 0. Then I will put this little Q minus 1, 1. This is my charge matrix. This will be T, this will be C. So as you can count dimensions, I will end up with Calabi fourfold. So my additional moment map here, it would be basically this moment map. So mu plus zeta plus square plus zeta minus square equal to C. So the moment map corresponding to this line. So what's the geometry of this guy? So this space you can think of as a fibration over C. So if I take my Calabi fourfold, I can think this is a fibration over C. And the combination is the following. So if I will thinking about my point in this bigger space X, zeta plus, zeta minus, I mean, of course, quotient by U1. Then when I'm going here and I put zeta 1, zeta minus, this is, you know, is invariant under this guy. So this remains. So I will have my Calabi fourfold fibered over C. Again, if you want to be more abstract, so you can just think that, look at this map. So what I'm doing is I'm having a manifold X, and then I'm just adding this C plus times C minus, and I have my moment map for my cut, and I'm writing something like this plus square minus, sorry, equal to C. And then I'm telling you that this space upon this U1 map, this will be a fibration. So this is a fibration over C as a space. So now if we look at fibers, what you can see, the following structure. So when zeta plus zeta minus is not equal to 0, you can actually argue that fiber isomorphic to original X. When you look, for example, zeta minus equal to 0, so you will get this space, right? Because you will have these conditions equals C plus zeta plus square quotiented by U1. So you get 1/2 of the, and then when zeta plus equal to 0, you will get another part. So your fibers generate and you get this cut. So you can naturally construct Calabi four. Okay. So I don't know what would be a good picture, but basically, if I look at vibration on this plane, so if I look that I have something like zeta minus square, zeta 2 plus square. So here as a fiber I have x, and then here as a fiber I will have this plus guy, and then here will minus guy. And of course here at origin I will have x0 sitting. Now what you can prove is the following, that actually this system, so this Calabi-Yau fourfold, if you write, for example, Picard-Fuchs equations here, Picard-Fuchs system here, so all objects which I gave you, FD, sort of another half volume, W, they're all solutions of Picard-Fuchs system here, but with different initial conditions. So Calabi-Yau fourfold controls both, you can write Picard-Fuchs. So this has been observed, I mean, again, not in equivariant setting. And I think by Meyer, then there were papers by Meyer and Lerche from end of 90s. But again, my understanding, it has been observed as experimental fact that people were trying to sell that if you calculate closed Gromov-Witten invariants for fourfold, then they're related to open, etc. So now all these objects are for Calabi-Yau fourfold. So what I'm telling you that if I want to do this symplectic cut in 3D, and I have all these objects I was writing to definitions, and you can ask which Picard-Fuchs system control them. The statement is it's a Picard-Fuchs system of not three-dimensional manifold, but four-dimensional manifold controls all these guys, and these are solutions of the same PD with different initial conditions. Okay. And you can, again, appropriately get both closed guys and open guys as solving this Picard-Fuchs system. Maybe I can. Well, next thing I can tell you, and this is the end of the story. Imagine I have two symplectic cuts, right? I mean, and then I can lift it to Calabi-Yau fivefold, but two symplectic cuts will intersect only along line, and that's it. So there is much richer Calabi-Yau fivefold picture. You can write this down. So I mean, the story is very, very much similar. So you can have two cuts, because only two cuts will generically intersect, and and also we have conjecture that there in Picard-Fuchs for two cuts we will have some annulus in between two toric brains also as a part of Picard-Fuchs system. But again, this type of statement is very hard to check except trivial systems, and when it's non-trivial, that very little information is available. And yeah. I think I will stop here. Thank you. Well, I don't know what's relative. I'm telling you that we can construct open Gromov-Witten. Maybe. I don't know. I think maybe these pictures are related, but I don't know. I wouldn't make any claim. again, here, what's important, what I would like to stress in all this story, which Luca was presented and I was presented, if you switch equivariants, I mean, all the story doesn't make sense. I don't know. Many people use equivariances just to calculate something and then set epsilons to 0 and get things. I mean, we are playing here different games. We are not counting maps. It just happened to correspond to counting maps. We define certain objects with certain properties, then we analytically them continue. We write special functions and checking the things. It's. I think one should be very, very careful saying that this is equal to that. I don't know. I mean, it's not that. Yeah, but it's a subtle thing. This is what Luca didn't have time to tell you is that, I mean, it's to extract regular parts, there is a lot of businesses going on. And if you do it wrongly, if you go 20 years ago, there were papers by Clem and friends who put in some, instead of integers, they get half integers. So basically, there are some lines of some of the tables which we can show you. You can put any numbers. I mean, it's a complicated story. One of the drawbacks when people look at Gromov-Witten invariants, they concentrated on 2, 3, 4 examples. But there are new features appearing. I mean, so this local Del Pezzo, Luca was referring, etc. It's a complicated story here too. I mean, there are some things when we cannot connect equivariant count to non-equivariant, whatever it. We cannot extract some lines of Gromov-Witten invariants story. You talk to mathematicians, they say, no, we can extract everything. So, and the conversation stops. I mean, they don't understand what we are saying. But there is 20 years ago, there was footnote, a paper where very, very much worried why they were getting half integers. I mean, they made some random choice and they got half integers. You can get any numbers in this. I mean, so there are some numbers in this tables of invariance which is not fixed. And to more complicated examples you go, the more troubles you will get on the way. And this is related to extracting these regular pieces. No, of course I can set up. I can set up. Spend 2 years of my life and set up any calculation. Yeah, I can set up. Then what? No. I think it does make sense. Yeah, but I mean. Mm-hmm. Right. Mm-hmm. Right. Well, the paper which is on the net, we showed this an example. So hard way we calculated, etc. Now what we are doing again, what we have to prove, we have to, you know how genus zero open stuff is related to a curve, right? You have to solve this equation, etc. So basically, what to prove is this in general, and hopefully the paper will come within this year. That you write this integral, you get very complicated Lorentz hypergeometric functions, and then Right, and you have to expand, and that's exactly correspond to solution. I mean, this solving guy on a mirror curve and writing, derivative of w equal to log of y of x, right? I mean, this is what, No, it's not fun. I mean, well, I don't know. It's whoever likes hypergeometrics. I mean, it sort of works, but of course it becomes very, very ugly, analytically. I mean, we don't doubt that it works, but to prove all cases. So I think most likely we will not prove all cases. We'll just show in a few cases, and then, because for this hypergeometric you have to use different expansion depending on regimes of this part and that. So it's. Mhm. What do you mean? Via. Well, C, you still have to do a mirror map, right? Right. So this is you get on the not. I mean, I'm not discussing mirror stuff, but let me just make some philosophical comment. So on a mirror stuff, it's not clear what's the geometrical object you get, but basically, you will be forced to come up with a formalism for multivariate perfect volume forms and learn how to integrate them. So I mean, that's we try to think about, but there are a lot of problems. I mean, you can go to covariant space, but then it's not clear what it means, etc., etc. Well, I don't want to go to this discussion very lengthy, but you can. There are different things when you can trade the values of Euler parameters to the equivariant parameter that you can do. But what exactly it means, I don't know. So in this story, that's what I didn't tell you. So what's happening is that once you start to cut Calabi-Yau, you actually don't get Calabi-Yau. You start to get low-dimensional Calabi and high-dimensional Calabi-Yau. So in full picture, I will have this hierarchy. I will get Calabi-Yau one-fold, Calabi-Yau two-fold, Calabi-Yau three-fold, Calabi-Yau four-fold, Calabi-Yau five-fold. So this is for cuts. I mean, so I take two cuts in Calabi-Yau 3, they will be cutted. If I sort of at everything, I will end up here. Some one cut corresponds to here. If I leave one cut correspond to this guy, etc. So there is whole things like this, and there are a lot of formulas you can write. I mean, conjecturally, I think that because the structure sort of respect cuts, then maybe it should work even to all genera, but of course this is highly speculative. I have no clue. No, right, but let me ask you, do you expect that topological strings will respect this symplectic cut on gluing? I mean, it's not, you will not expect this to. I don't know, I'm not making any claims, but what I'm saying is that if in principle, you will think that topological strings corresponds to some form of symplectic invariance, and I'm not expert, I mean, then some of the structures, this should survive at least in some form. Yeah, further information, right. And of course, here I didn't talk and Luca didn't talk, but we can do everything K-theoretically. That's not a problem. Even certain formulas looks nice in K-theoretical version.